Okay, so in this problem, we will study the effects on a beam of a distributed load that is just a rectangular distributed load all the way from the beginning to the end of the beam. Um, the first steps, that will be, well, that will be those first steps. First steps, that would be, because it's a distributed load, we need to find the force, resultant force, FR. Oops. So the force resultant for a distributed load, that will be FR equal the F time the distance. So in this case, FR equal 2 kilonewton time the total distance on the beam, that's 15. So that will be 30 kilonewton. So we can replace this distributed load by one load. It's in the center, right? Because it's a rectangular load. So we have one force of 30 kilonewton. And we need to find, the second step, that will be to find the reaction force. So I will put it there, reaction force. And for that, we need to do a free body diagram and equation of equilibrium. So the force that we know is 30 kilonewton. The force that we don't know, that will be, oops, try to put them as large as the other one. That will be AY and BY. At A, we can technically also have a AX, but it's 0 because there is no normal force anywhere. And we need to look at the distance. So we have this distance there, 5. The distance between this one and this one is 2.5 because it's in the middle, 2.5 and 5 again. Okay, everything is meter. So let's do this equation of equilibrium. We like to do moment to solve for one of the things. So sum of the moment about A equals 0. We got minus 30 times 2.5 and plus by times 5 equals 0. So we got by equal basically 30 divided by 2 equal 15 kilonewton. And we can do sum of the forces on y equals 0. So we have ay minus 30 plus 15 equals 0. A wall equals 15 kilonewton. This is symmetrical, and you will also have in your quiz something symmetrical, so you need to find the same forces. In the slide, I showed you the effect of not having a symmetric connection, to have your two connections to different places. But in our case, we keep them symmetrical. It's a good way to check that we have the correct value, the correct diagrams. Everything should be symmetrical by the center. Okay, like not symmetrical, but yeah, the shearing will not be symmetrical at the center, but they will look like similar. Anyway, step number 3. Step number 3, we will need to divide our beam in 3. Everywhere divide the beam. So we will divide them everywhere we have a jump, a force that is applied. We need to stop it. So we will separate the beam at 5 meters and 10 meters. So we will study 0 to 5, 5 to 10, and 10 to 15. So we will find the shearing force equations and the bending equations for all of them. Before we do that, before we do the equations, let's try to find the shape, the overall shape, and all the information that we can just graphically. That will be a very good way to, after that, to check our equation. Let me move that there, and we will do the equation. First thing that we can do is the shearing force. We will have our axis like this, and this is our axis X, and we can, oops, put down the 5, the 10, and at the end that will be the 15. Okay, so what is happening on our beam? First part of our beam, let me, oops, put it in yellow. First part there, what we have is a distributed load that is with like a slope of 2 kilonewton per meter. Not a slope, but yes, that will be a slope for the, that will end up being a slope. So what's happened at the very beginning, we have 0 force. Every meter we add 2 kilonewton. So what's happened that will look like something like this. Getting down, getting down, getting down. This slope is -2, so -2x. And we stop at 2 times 5, I'm -10. So this point there will be -10. After that, we have a bump with AY, and let me write it, AY equal 15, BY equal 15. So there we will go up of 15, so this distance there is 15, and we stop at then 5 kilonewton. Now we have again the distributed load from 5 to 10 with the same slope. Okay, so we will go down like this. Oops. So slope is -2x for the second term of the equation. We will find that with the calculation. We don't need it now. But what we know is like, we know at the end of the beam there, at the end of the beam, we know there is no external forces, nothing that is applied. So we need to end at 0 at 15. And we know the slope is also -2x. So here we go, like this. This is maybe a little bit too steep. You just make it a little bit less steep. Up, -2x. And it's -2x for 5, so this one should be 10. And now between both of them there, we have +15, the by. And so this diagram is, I can make it bigger. This is the in kilonewton, and this is the force, the shearing force, okay, in kilonewton. Let's find, I know the equation is not just -2x, we will find it plus blah, 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 and plus blah, blah, blah. We will find it with the equation. We can also solve it graphically, but let's do it with the equation. For the bending, I will do another graph, oops, like this, and I will move down my 5, 10, and 15, so 5, 10, and 15. Should we find a negative or a positive bending? What do you think? Let's look at our beam. So if we apply, the question is our beam, is this our beam this way? Sad guy? Can we do it something like this? Or is the beam this way? The happy guy? Doop, doop. Okay, or the happy frog? Like a happy frog. Which one do you think? If we look at the distributed load, there's more chance that is this way. It cannot be this way. What it could be this way. Something like this. Depending of the position or reaction forces, like this is the, like the connection, depending on that, it's possible that in the middle is positive and on the side is negative. It's possible. We can check. Most probably this is negative on everywhere. Most probably. Okay. But definitely it cannot bend up on the side. It has to bend down at the beginning and at the end. So let's look at this one. We have a negative shearing force. So if it's negative, I will use another color, the bending moment has to decrease. If the slope of the shearing force is -2x, this one will be the integral, that will be -2x squared divided by 2, so -x squared. So it will look something like this. Okay, I try to make a nice, something like this. So it's decreasing and it's second degree order. All of them will start by something with -2, -x squared, all of them. So this one decrease. After that, the shearing force is positive, and where we have a shearing force equal to 0, we will have a maximum for our bending moment, because the derivations of the bending moment will be the shearing. So the derivation of a slope that is flat is 0. So we will have something like this. Oops, and it's symmetrical. And after that, again, symmetrical, that will be this way. So shearing is negative at two different places where the bending moment decrease, and the shearing force is positive, and that's where the bending moment increase. So most probably it will stay negative. It could be, depending on the location, we don't know, we're just looking at it. It could be something like that. Up, up. Maybe the bending could be positive. We will check with our equations, and again, you will see examples where the bending gets positive on the slide. I put a few scenario where changing the forces and changing the location of the connections will change if the bending gets negative or positive. I will remove this one so we don't get confused at the end, but that's what I expect. That's the graph I expect. Now, let's see if we get some equations that are making sense with that. Okay. So I need this, from 0 to x, a 0 to 5. What we need to do is we need to redo a free body diagram for all of those different space, like step. So we have the distributed load on the top. Don't use the reaction force. We need to find the new reaction force. We know the distributed load is 2 kilonewton time meter. We know that distance will be x, and there is no reaction forces below because we are before the point A. Okay, this is just this way. So this is what we know, and now what we don't know and we need to find is the internal forces. So when we cut to the right, Vx is down, and x is always outside, and mx is positive. That's our free body diagram. We can replace the distributed load, and I don't like to do that. I like to do it down. I will do it down. Sure, I've done that before. Our distributed load on the top will be 2 times the distance, so will be 2x. The distance from that side will be x divided by 2. And let me redo our unknown Vx, Mx, Mx, and Nx. So we can do now the equation. Sum of the forces on y equals 0. We get minus 2x minus Vx equals 0. This is V1, okay? And this is about x. It's like a V1 of x. That's a function of x. So V1 of x equal, oh, I'm missing a minus 2x equal minus 2x, okay? And this is what we know already. This one is this one. There. We already know that it was minus 2x only, okay? And for the equation of moment, so sum of the forces on x equals 0, this one equals 0, okay? We got that. Sum of the moments we'll do about the point x equals 0. So we have the force 2x times the distance x divided by 2 that create a moment that is positive, and the moment mx is also positive. So m about x equals 0, and that's the m1, the first equation. So we have m1 of x equal minus x squared. Okay. So this equation there is this one. Okay. This is minus x squared. And we can find the value of the moment with that equation. So moment about 0, we get minus 0 squared equals 0. That's normal. There is no outside moment. And the moment at 5 equal minus 5 squared, so equal minus 25. So this value there is, oops, let me remove that. It's minus 25. Those values are kilonewton time meter. Okay. So this is minus 25. That will be minus 25 there too. So this is from 0 to 5. Let's do now from 5 to 10. It's a bit more difficult, okay? So we will do step B from, we'll make it bigger so we can see, from 5 to 10, okay? And even if we are from 5 to 10, we draw all the beam from 0 to somewhere in between 5 and 10. So free body diagram. we have the distributed load. Okay, that is 2. We have that distance, that is x. And we have the AY at 5, that is 15 up. So we have 15. Okay. This free body diagram is equivalent to this. Oops. 15 distance x. No, distance x, sorry. Distance 5, distance x. And there we have the force that is equal to 2 times x. So the distributed load times the distance. And this distance there will be, because it's, so on that side, it will be x divided by 2. Okay, let me try to put that on that side. Okay, and we have Vx down, Nx to the right, Vx up. Mx. So let's do our equation. Sum of the forces on y equals 0. We have minus 2x plus 15 minus v2 of x equals 0. So we have v2 of x equal minus 2x plus 15. Okay. This equation is v2x. This is this one. So now we know that here it's plus 15. Oh no, I hate that when I do that. Okay, plus 15. So now we know that this equation is plus 15 there. Okay. Oops, I just check my value. Here we go. Here we go. And we can do now sum of the moment about, let's say, x equals 0. So we are about that point. The 2x create a positive moment times the distance x divided by 2. The 15 create a negative moment, so minus 15. And this distance there, it's x minus 15. X minus 5. X minus 5 times x minus 5, and mx is positive, so plus m2 of x equals 0. So we get m2 of x equal, we switch them sides, so minus x squared plus 15 times x minus 5, that we can write minus x squared plus 15x minus 75. So this equation is the equation in the middle. It's this equation there. Oops, let me write it. Minus x squared, we say plus, what did I say? Plus 15x minus 75. Okay, and we can check the value at 5, at 10, and at, what will be interesting is to find this value. Is this value positive or not? Is the maximum of this curve between 5 and 10 is positive or negative? This is at, we will be at 7.5. So what we can do is we use the function that we found. So m2 of 7.5 equal minus 7.5 square plus 15 times 7.5 minus 75, and we got minus 18.75. Yes. So this value there is minus 18.75. So in fact, this equation is a little bit more like this. Let me draw it like this, right? Because minus 75.5 is not super away from 75. This way. And this one is the maximum increase decrease. Okay, and this is my equation pink. And now we are missing one last equation. Let me see if I can get organized to the right. Step C, we can do from 10 to 15. So now we can do from 10 to 15. So we will find the function from 10 to 15. We have to draw the beam, one of the side of the beam. We can use all the way from 0 to x or from x to 15. I think in that point it's a little bit easier to do the right side because that's just what we have left. So that will be the distance, x will be there, and that will be the distance 15. We have the distributed load on the top. Again, that is 2. And we don't have any force on the bottom. So this one will be, and we have the unknown forces. And just be careful for the internal forces. That's where we need to switch the sign because we cut the left. We are looking at the left side. So Vx is positive, Mx is in that direction, and Nx is going outside the normal force. So this one is equivalent to, I will put it down. I think that will fit better. Yeah, not there. Okay, so the distributed load there is 2. The resultant force of the distributed load will be 2 times the distance there, that is 15 minus x. So time 15 minus x. This distance there will be 15 minus x divided by 2. Okay, be careful of those distance. And after that we have Vx up and x mx. And we can do our equation. So sum of the forces on y equals 0. We get plus v3 of x, it's positive, minus 2 times 15 minus x equals 0. So v3 of x equal 2 times 15 minus x. So v3 of x is minus 2x plus 30. So this one is, let me use a new color, let's do green. Minus 2x plus 30, this is this one. So now we found the value of the equation there. Plus 30, that makes sense, that is larger than the one in the middle. And the minus 2x, we are happy with that. That's the slope. The slope is the same because the distributed load is the same everywhere. And one last equation for the moment. Sum of the moment about x equals 0. Let's do about x. So what do we have? We have minus mx, m3x. So this time the moment, the internal moment is negative because it's clockwise. And also the force distributed load or reaction forces, not correction, the resultant force create a negative moment. So minus 2 times 15 minus x at the force times the distance, that is 15 minus x divided by 2 equals 0. So we have m3x equal minus, let's write it, 2 divided by 2 times 15 minus x square. So m3x equal minus 15 minus x square. You can develop or you can keep this way. What is interesting to see is when we replace x by 0, so by 15, m3 of 15, we get 0, and that we want because we are at this point. And this is the equation for this part of the moment. And I can write it there. Minus, oops, what did I do? Minus 15 minus x square. I recommend to take the time to take your calculator and draw those functions. If possible, just from 0 to 5, 5 to 10, 10 to 15, that will be easier. Or you can use any online software. That will be a very good way to check that your equation makes sense. Try to find the moment with your equations at the same point. So with M1 at 5, with M2 at 5, and with M2 at 10 and M3 at 10, just to make sure that you have the correct value. Otherwise, it's not correct. And what we can see, and it's usually the case, is like the largest shearing force and the largest also bending moment are at the point of contact where you have the connection. It's either where you apply an external load, either where there is a reaction forces. So this is the first part of the problems. You will have the second part in another video. I hope everything made sense. Bye bye.